Well, hello everyone. This is our video to cover section 16.7, surface integrals in 3D. And there are, I believe, 8 questions in this section now. They fall into 2 categories. The first type of surface integral is going to be written like this. So the double integral over a surface of a function f of x, y, and z with respect to the surface S. That can't really be evaluated in that format, but what we can do is we can convert it into this fella here, which is a bit ugly, I understand, but it essentially gets the job done. So instead of this expression, which will have x, y's, and z's in it, this bit here essentially says you convert it to x's and y's. And so how do you replace the z? Well, z is going to be the equation of the surface, so it's going to be z equals x squared plus y squared, or z equals 4x plus 2, whatever it might be. So that's the surface, and that is going to go here. Then you have to follow by this essentially correction factor, which is the square root of this guy squared plus this guy squared plus 1. And if you're wondering where the plus 1 comes from, it's actually dz by dz squared, which is itself, so 1 squared, which is 1. So let's see if we can talk a little bit about how we can evaluate such an integral. So there's only 4, so I'm going to start at question 1. The surface integral we're being asked to calculate is this one. And the information that we've been given is that the surface is the plane 1 plus 2x plus 3y. And the region D is the part of this surface that's on the floor that's being projected up, and that's what we are essentially looking at. So can you imagine you have your XY plane, and the region D might be here. And then you've got your surface doing its thing up here. Well, if you project this up, you can imagine that that represents the surface S. And then on that surface S, we're evaluating at every single point on it, x squared, y, and z, and building that surface integral up. So can you imagine this might represent the temperature at any given point on that curved surface, S, and we're essentially summing them together, getting the total amount of heat energy, magnetism, whatever it might be that's being measured. So we need a few bits and pieces. First thing I'm going to identify is that the function z is this guy. So that's who g of x, y is. So that means that my double integral is now going to be x squared y times this guy, 1 plus 2x plus 3y. Now, what does the region D look like? Well, they tell us in this question that it's basically a rectangle, and it's written in this way, which we all know basically means that x, because x goes first, is between 0 and 2, and that y goes also from 0 to 2. So I know that this integral is going to be x equals 0 to 2, y equals 0 to 2, times the square root, and we're going to go dx dy. And inside this square root, we differentiate this guy with respect to x, which gets me 2, and then I square it. With respect to y, which gets me 3, then I'll square it, plus 1. So this surface integral has now been converted into this equivalent double integral. The value of this double integral would be the value of that surface integral up here. So I'm going to only take this a little bit further. Y equals 0 to 2. X goes from 0 to 2. This expression here is going to be x squared y plus 2x cubed y plus 3x squared y squared. And this is 4, and that's 10, so it's the square root of 14, which I'm just going to pull out at the side there. and we can then do dx, dy. And at this point here, I'll leave it, because essentially you're just going to do a rather long and clunky double integral. If you do it correctly, it's 128 square root of 14 over 3. You can see where the square root of 14 is coming from. So essentially this bit here should be that fraction. And that's our first one. Now, in question 2, we're going to be looking at the surface integral. And it's xz ds. And we're told that the surface has the equation 2x plus 2y plus z equals 4. And we're also told that it's in the first octant. So for this question, I am going to have to find g of xy from the equation here. I'm also going to have to find what the region D looks like based on this information, and it's in the first quadrant. So I won't even worry yet about what this is until we get all that other information. So let's go looking for the equation of it. Well, that means z equals, in this case, 4 take away that guy, take away that guy. And we now have our g of xy. Check. Now to find what the region on the ground looks like, right, the D guy, it's a little bit trickier, because essentially what we're interested in this question at least, is what does that thing look like as it projects onto the ground. So since I'm in the first octant, I only need to worry about positive x and y's. Now, if you go up here, you can find out where this surface cuts the x-axis, and that's when everything else is 0, so x equals 2, which takes you to here. And by the way, y is equal to 2 takes you to here. And so the region D is going to be that triangle. Well, I'm going to set up the limits of integration. X is easy, 0 to 2. If you imagine a vertical strip here, I need to find the equation of that line in the form y equals. Well, I can tell you its slope is -1 by just measuring rise over run, so that's -x, and it passes through the y-axis at 2, so there is our guy. So the y values also start at 0, and they finish at -x add 2. And that represents region D, and that's that done. And this guy is our g of xy. So when we put all the pieces together, we're going to have the integral from x goes 0 to 2, the number has to go on the outside. The y is going to be 0 to -x add 2. The function that we've got here is xz, and z is this guy. So it's going to be xz becomes this guy, followed by the square root fella, and a dy first, followed by a dx after that. And this guy is going to be the derivative of this guy with respect to x, which is what, -2, and then you square it. And this guy, derivative with y, and then you square it, plus 1. 4, 4, and 1 make 9, square root of 9 makes 3. So we now have this integral here. And 3 times x times that guy gets me 12x. 3 times x times that guy gets me -6x squared. And 3 times x times that guy gets me -6xy. And then we'll do a dy and a dx. And at that point, I will leave it. And allegedly, that comes to 4 if you do it correctly. And that's the second situation done. Now, in the next question, I'm going to do a little bit less. In this question, you're being asked to find the surface of x ds. And we're told that S, the surface S, is actually a triangular region using these 3 points. So if you can imagine what that might look like. One zero zero is here. 0, 0, negative 2 would actually be over here. And 0, 0, 6 would say be up here. And so they're talking about this surface here. So if you give me 3 points and you tell me those 3 points make the surface, you know it's a plane. You can find the equation of that plane by calling this, say, P, this guy Q, and this guy R. And you'll find the vector PQ, and then you'll find the vector PR. And then you'll get the normal vector, which is the cross product, is the cross product of PQ and PR. And then you can use the fact that N dot XYZ will be equal to N dot any point up at P, 0, 0, 0. And when you're finished doing that entire operation, you can check it. You will get Z equals 6, take away 6x plus 3y. So we have took a lot of work, but we've now found out what the function g of xy is equal to. Now you want to know what the region D on the floor is. It's basically, I'm not going to shade it, but it's this bit in here on the floor. So if I draw a little x and y axis of what that region looks like, it looks like it passes through x at 1 and it passes through y at negative 2. So it's this triangle here. So I now need to get the limits of integration of this region here, which is D. Well, I can do the x's. They go from 0 to 1. And the y's, well, if you imagine a typical rectangle, they go from 0 to the equation of that sloping line. And if I do a quick count, it's a 2, 1, it's a 2x, because its slope is 2, and it takes away 2. And that guy now represents our region D. So we have everything we need to set up the integral. So it's going to be the integral from x equals 0 to 1, the integral from y equals 0 to 2x, take away 2. The function that we're integrating is pretty boring, it's just x. And then we can put in the square root part. Well, for the guy I've got here, if you differentiate them with respect to x, you get negative 6. If you differentiate them with respect to y, you get 3, and then you add 1. In this case, it's a dy dx. So I'm going to have an integral from 0 to 1 and 0 to 2x, take away 2. And that's 36, oh God, 9, 45, 46. Square root of 46 is not very interesting, so I'm going to pull it out and just do a dx, dy dx. And I'll dot that. But evidently, if you do it, if you do it correctly, you get the square root of 46 over 3. And that's essentially the end of that one. Now, the theme I'm detecting, you might have noticed as well, is that the planes that we get to deal with, at least so far, have been very simple ones, where it's basically the z is a plane, so the derivatives end up being numbers, and so the square root is not that particularly pretty. The final one is much messier than that. We're going to find a double integral, a surface integral of y. That's nice. Now, what do we know? We know that z, which is essentially our g of xy function, is equal to 2/3 x to the 3/2 plus y to the 3/2. And the x's are simply 0 to 4, and the y's are simply 0 to 3. So, I mean, they are being really nice to us, at least partly. Let's find dz by dx. Right, well, if you multiply that out, you get 2/3 x to the 3/2 plus 2/3 y to the 3/2. So that's much easier to differentiate. This fella then will be, x to the half. And this guy, y to the half. So we should be ready. The x's go from 0 to 4. The y's go from 0 to 3. The guy is y, so I don't need to change anything there. Square root of this guy squared plus this guy squared plus 1 dy dx. Now that becomes x equals 0 to x equals 4, y equals 0 to y equals 3, y times the square root of x plus y plus 1 dy. And that is a problem. We have to integrate this. So I would suggest a way to tackle this question would be to do a u-sub. And the u-sub I would choose would be x plus y plus 1. Because when you differentiate this guy with respect to y, because that's the guy we're interested in, you just get 1. So that makes du dy. And I'm just going to focus on this integral. Forget about the other guy for a while. Right. So the y equals 0 to y equals 3, y, the square root of x plus y plus 1 dy. We'll just focus on that guy. So it's going to be the integral of y times the square root of u, and the dy just turns into du. So that's pretty good. Big problem is that we've got a y left over. Well, if you look at y here, doesn't it, eventually you can rewrite it and say that y is u minus x minus 1. So u minus x minus 1. And the square root of u, I'm going to call it u to the half du. So we're now going to get u to the 3/2, take away x u to the half, take away u to the half du. And it's okay to have x's because they're considered constants. It wasn't okay to leave that as a y because y was being considered a variable. So if you're wondering why I needed to fix this, but I could leave that alone, that's the reason. Now, add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. Add 1 to the power, and divide by the new power. Then replace the u here with square root of u to the 5, 2/3 x square root of u cubed take away 2/3 the square root of u cubed. Then I will replace the u with the square root, instead of u, x plus y plus 1 to the 5. Take away 2/3 x, the square root of x plus y plus 1 cubed. Take away 2/3 the square root of x plus y plus 1 cubed. And that can be evaluated at y equals 0 to y equals 3. Now, if you put in 3, you're going to get 2/5 the square root of x plus 4 power of 5. Take away 2/3 x, the square root of x plus 4 cubed. Take away 2/3 the square root of x plus 4 cubed. Minus, if you plug in 0 here, you get 2/5 the square root of x to the 5. Let's check it. Plug in 0, x plus 1 to the 5. Take away 2/3 x, x plus 1 cubed. Take away 2/3 the square root. What would you get if you plugged in 0 here? X plus 1 cubed. And that horrible mess can now be added. Well, I don't think you can tidy up much. Can be added to here. And I'm just going to go dx. And if you look at each of these pieces, you can rewrite them in a way that is going to make it easier to integrate. I know it's not pretty, but you're going to get that guy. That guy. That guy. Take away that guy. Take away this guy. Finally, take away this guy. This guy you can do very quickly. It's basically, I wouldn't do a u plus 4, but if you did, it would work. I would just basically add 1 to power and divide by new power. This one, you'll have to do a u sub of x plus 4. This one you can do easy. This one you can do easy. This one you do a u sub x plus 1. And this one you can do easy. And believe it or not, because I am definitely not going to try that one out, that should pay me more money. It ends up being this expression. And that's the end of that one. That last question is ridiculously big, but I just put it in because I don't want to get used to too easy a question. So that's both extremes. I think the planes that we did, questions 1 to 3, were pretty straightforward. And that last one was ridiculously ugly. Now, we are finished with that kind of surface integral, and we're now going to replace it by the next 4 questions, that one. And the surface integral are going to look like this. And you're going to be told what f is, and you're also going to be told what the surface is. Well, what you can do is this surface integral can be evaluated by this formula. It's still a double integral. The region D is the same as it was before, but look, no more square roots, which actually makes life 10 times easier. Now, D is going to be the region on the floor that's projected upwards to meet the surface coming like this. Z is going to be the equation of the surface. and f is going to be a vector field. And the vector field will have an x, y, and z component, and these guys I'm calling p, q, and r are all going to be functions typically of x, y, and z. So start off with hopefully a nice simple one, version of 5. We must to find this guy. By the way, he is called the flux for some reason. Its full title is the flux of F across S. So evidently the engineers amongst you know, or will eventually know, a term called flux, which you would probably be interested in finding. Now, in our question, the information they give me is a vector function, and it's vector field xy, yz. Oh, it's got a lot of symmetry in it, zx. So your p, your q, and your r. Check. And the surface z, they have told us, is 2 take away x squared, take away y squared, and that's the function g of xy. And the region D in this question, they also tell us, and it's actually a nice little rectangle. 0 to 1, oh, it's actually a square, 0 to 1. And that's all the stuff you need. Time to adapt it to that situation there. So it's going to be a double integral from x equals 0 to x equals 1, from y equals 0 to y equals 1, then negative p, so negative xy, times the derivative of this guy here with respect to x, which gets you another negative 2x. Take away q, which is this guy, yz, times the derivative of g with respect to y, which happens to be negative 2y, plus r, and r happens to be, in this case, zx. Let's see what we get. Multiply all this out and you get 2x squared y. Multiply all this out and you get 2, positive 2, y z squared. And you get zx. Now, the integral that we've got doesn't have, or isn't allowed to have z's. So what we have to do is we have to replace the z's, right? And I better check one of these. That's just a z, isn't it? Yeah. So I think one of these terms is not right, and I want to figure out. It's that guy. There we go. Found it. There. These two z's aren't allowed to stay there. How do we change them? We change them by replacing them by the surface formula. So what we now have is the integral from 0 to 1, 0 to 1, 2x squared y plus 2y squared z, which is this guy, plus a zx, which is this guy. And then you can do your dx dy. Not much left to do here. Multiply this guy out and you get 4y squared. This guy, negative 2x squared y squared. This guy, negative 2y cubed. This guy looks like a 2x. Take away an x cubed. Take away y squared x. And then you can do whatever I decided, dy dx. Now, I know that is ridiculously big and ridiculously ugly, but it is doable. It's just a normal double integral. I don't see any variables separable, so you'll have to do it the long way and according to the answers in front of me. It's 293 1/80ths when you're finished. Now, setting up 2. In the question, you're told negative x, negative y, z cubed. So there's your p, there's your q, there's your r. You're also told what the surface is. It's the square root of x squared plus y squared. So that's my g of xy. And the plane is also got an extra piece of information, which is z equals 1 and z equals 2. And you might think, well, what on earth is that going to tell me? This piece of information is going to tell us the floor. So let's focus on the floor. If you have this guy and you make z equals 1, then at that slice, this is basically a cone, is going to come out as a circle of radius 1, center of the origin. And then if you do z equals 2, I know it looks like a z, but it's one of my 2's, you will get x squared plus y squared equals 4. So I now know what the ground looks like, the xy plane. And it is a circle inside a circle. And the little circle is 1, and the big circle is 2. And so the region D is one of these donut shapes. So that's going to influence what I'm going to be doing later. Essentially, I'm pretty sure I'm going to have to go polar to do my double integral. But let's not worry too much about that yet, because we still have this guy to calculate. So I'm just going to call it a double integral over D, where D is this donut shape. It's then going to be negative of this guy, which is x. And if you differentiate this guy here, right, with respect to x, you will get 1 over, oh, let's do that at the side, because I'm pretty sure it's nicer than I was about to write. There's z, which I'm going to call x squared plus y squared to the half. So if I want to do a partial derivative with respect to x, it's multiply by the power, reduce the power by 1, and then finish with the derivative of the inside function, which is 2x. The half and the 2 cancel, we get this, and this guy on the bottom becomes that guy, which in turn is going to be that guy. Okay, so now I know the dg by the x. It's actually an x over the square root of x squared plus y squared. Okay, then take away q. So take away makes that a plus, so you get y. And the derivative I get guarantee because of symmetry is that guy. And then you're going to add r, and r is z cubed. Well, I know I'm going to turn that z cubed into x's and y's, so I might as well just do it right now. That z, so I'll cube it. And we'll do a dx dy. So this guy and this guy do simplify a little bit. Let's see what we get. We get a double integral over a donut of x squared over x squared plus y squared. Add a y squared over the square root of x squared plus y squared. Plus, and I'm going to rewrite that guy a little bit differently, the square root of x squared plus y squared cubed. We'll call it dA. These two can join together and give me x squared plus y squared over this plus that guy. dA. That partially cancels this guy. And so I'm left with a x squared plus y squared plus the square root of an x squared plus y squared cubed dA. Okay, I think it's time to go polar. All right. To generate this fella, the radius will have to go from 1 to 2. But since it's entire revolution, theta can go from 0 to 2 pi. That guy is basically the square root of r squared, so he's r. This guy is the square root of, well, figure that guy out as r, so you're going to get r cubed. Then you're going to have an r dr d theta. And that would become 0 to 2 pi. R can go from 1 to 2, and r squared plus r to the 4 dr d theta. And then we got lucky because it's variable separable. And allegedly, the answer is negative. Okay, and it's negative 256 over 15 pi. Rather weird number, and that's what they say it is. If you get a positive answer when the answer should be negative or vice versa, it's probably caused by orientation. And when you do surface integrals, there is a thing called positive orientation outwards, and there are a thing called negative orientation, which typically is inwards. So if you see the word positive orientation or outwards orientation, realize that your integral is the one you want. And if you get a negative one, stick a negative in front of it and that'll fix the problem.